Welcome, everyone. So this is going to be a synopsis of a number of the videos that I have on my YouTube channel at Dr. Jan 41 about climate change and the threat that it faces. So welcome to those watching at home. Welcome to those who are here. First off, and as I go through this, this will kind of be the abridged version, because as you'll see, I have a lot of videos. And I'll just kind of hit the main points on each one. Obviously, anyone here, if you have any questions, we can diverge and go into other topics. So the first comment, obviously, is greenhouse effect. Yay! I mean, obviously, we love the greenhouse effect. We wouldn't be here without the greenhouse effect, because all of this energy comes here from the sun, and that's great. But then it bounces off and goes into space. If the only thing that determined the temperature of our planet was the distance from the sun, Venus would have a temperature of about 100 degrees Celsius, and we on Earth would be about -18. So there would be no liquid water on Earth, and there would be no life on Earth. Certainly, I mean, not the way that we know it, unless we were talking about deep underground, et cetera. But because so much of the sun's energy doesn't escape into space, but rather it's kept around the planet because of heat trapping gases, the actual temperatures of Venus are 450 degrees Celsius, and the actual temperature of Earth is 15 degrees Celsius. So greenhouse effect, yay, we wouldn't be here without it. So our planet and life on it depends on those heat trapping gases. But then the problem is these heat trapping gases can change. They've certainly changed over time, and we humans are changing them. So then that's the issue to be debated. So just real quick, there's all of this energy reaching us from the sun. There's all of this visible light, ultraviolet light, etc. But once it interacts with the molecules here on Earth, what then is outgoing to space is what we call infrared radiation. Now, infrared radiation, I mean, the fancy word for that is heat, but it is a form of electromagnetic radiation, same as light and ultraviolet light. The only difference is what's called the wavelength. So these wavelengths here in microns of 2 through 16, that's what we call heat. So just pointing out, when we talk about heat or infrared radiation, there are different wavelengths. That becomes important in just a second. Now, Professor Zaravja, that is a wonderful green shirt you're wearing there. And there's a reason that it's green, because molecules interact with different forms of electromagnetic radiation. So they will absorb some and reflect others. So when I look at this shirt, if it looks blue, or if this shirt looks green, it's because green light is bouncing off that shirt into my eyes, but it's absorbing, say, blue light and red light. And so molecules interact with these different forms of electromagnetic radiation, absorbing some and reflecting others. And we're familiar with that on the visible spectrum. We're certainly aware of this with ultraviolet light, because whenever I go out, I wear sunscreen, because I don't want my DNA to absorb UV light, which might cause mutations. So there are molecules which can absorb visible light. There are molecules which can absorb ultraviolet light. And then there are molecules which absorb heat. So here you see heat coming off of people. It's a form of radiation. And just as there are molecules that specifically absorb specific wavelengths of light or UV light, the same then is true of heat. And that gets us to greenhouse gases like number one, water. Water vapor is the number one greenhouse gas. And once again, greenhouse gases, they're not bad. We wouldn't be here without it. And water is the most abundant of those heat trapping gases. Now, so here we can see a lot of cloud cover. These clouds are absorbing a lot of the heat that would otherwise be lost up into space. Now, it's really not me, saying anything crazy that water is a heat trapping gas, because technically, any molecule that has more than 2 atoms can absorb heat. So let me repeat that. Technically, any molecule that has more than 2 atoms, because while you then have the molecule, there are phenomena known as bond bending and bond stretching, which occurs. And so water, because it has 3 atoms in it, as energy hits it from the infrared spectrum, will cause some of this bond bending and stretching. And then as energy comes off the water, it goes any which way. All right, so this energy at first is going straight up into space, but as it radiates off of water, it goes any which way, including some back to Earth, helping to trap heat. So water absorbs heat, but if, remember, there's different kinds of heat, different wavelengths. The question then is, which heat does it absorb? And the answer is there are some wavelengths absorbed by water, I don't know what just happened there. I'm sure we'll come back. I don't know what that's about. There are some wavelengths which are absorbed by water, and then there are others which aren't. There are what we call windows, all right, where heat would pass up into space because water vapor doesn't absorb it unless something else does. Welcome. So does anything else absorb heat? Especially, does anything absorb heat in these windows, in these spaces where water doesn't? And the answer is yes, there are a bunch of things. Carbon dioxide is one of these. So if you were to ask, what does carbon dioxide absorb? Once again, this isn't something which is debated. It's easy to say, all right, let me take a container of carbon dioxide, pass energy through it, and see whether all of the energy I start with passes to the other side, in which case carbon dioxide did not absorb it, or if it doesn't, all right, if some of the energy is absorbed. So this is easily measured. Carbon dioxide absorbs some wavelengths of infrared and not others, including some of these which are in these windows. So the more carbon dioxide we have in the air, the more heat which will not pass into space and be retained in our planet. So carbon dioxide is a greenhouse gas which absorbs heat. Now, on the videos in my YouTube channel, I have some which are serious, some which are quasi-serious, some which are songs. And so, there's kind of a variety of them. One here, and I'm sure you'll get the idea in just a second. We have some people gradually reacting to some thoughts on gases becoming more and more shocked as time goes on. The thing that they're reacting to is if there are these heat trapping gases, what's happening to them? And the answer is quite easy. They go up and up and up and up, period. So each year we hit record highs in carbon dioxide. I'll be talking about a few others in just a second. Each year we hit record levels of methane and nitrous oxide. All of them are doing this. And this is kind of, my favorite to talk about because I am quite aware of the fact that I'm old. I am old, but I'm not that old, especially when we're talking about the planet in that sense. Like my lifespan, it's been a while, but not been a huge amount. If you look at where carbon dioxide levels are now, they've broken 400. Actually, that was a number of years ago. When I was born, they were around, 320 or so. So in other words, carbon dioxide is a heat trapping gas on a planetary scale. About a quarter of it is new in my lifetime. Like I'm old, but I'm not that old. A quarter of it new in just my lifetime. That's a big amount of change in just a small amount of time. I'll come back here to talk about methane and the rest, and you'll see some of those people. They're getting more and more shocked. Now, this is kind of a yearly, yes?
How does our current levels of carbon dioxide compare with levels during all of human civilization?
Oh, excellent question. So quick answer, and then I'll have a slightly more in-depth answer. Far higher. All right. So we have not seen anything this high since interglacials. And then, a short answer there is one of the big questions about climate change is not whether it's going to happen or whether it's going to be bad, is why isn't it so much worse? Why isn't it so much worse? And their answer is like, well, the oceans must be absorbing more than we thought they were, and are there limits to that? But good question, we'll get to this again in a second. But if you look at the difference in carbon dioxide levels, heat trapping gases in the atmosphere between when there were interglacial epochs, which were warmer than they are today, versus the glacial epochs, and here I am in Northeast New York, 12,000 years ago, the amount of ice outside the window would have been a third of a mile up. So if I was standing on the ground 12,000 years ago, right out here, I would have been a third of a mile higher. Stepping on a piece of ice would stretch to the Arctic. All right. So the difference in carbon dioxide levels is about this. All right. But this is a huge difference. Why aren't we seeing much? We haven't seen interglacial versus glacial epoch levels of change. But then the fear is that coming? And by the time do we start to see that? Is it too late for our children and grandchildren to reverse it? That's the fear. So great question, and I'll get back to that in a second. Now, because each year is kind of, oh, I'm sorry, I wasn't done. Each year is a record. Then I have a lot of videos because 2018 record year, maybe I make a video, and then 2020 record year. So obviously, I'm just going to skim a lot of these. We could go by year, or you could go by month. And so that's kind of interesting. So let's go by month. So here's January, February, and 2018. All right, then 2019 comes around. Each month is higher. 2020 comes around. Now, we did, if you notice, there was a bit of a reduction because with COVID, there were fewer vehicles, and it was measured. Carbon dioxide levels as far as emissions, because we're burning less fossil fuels, they actually went down a bit. 7% was what I read. So you'd think, wow, great, that's helping the atmosphere. Well, it did. So the increase, if you notice the difference between the purple and the red dot, not quite what it was between the orange and the purple dot, but notice it didn't go down. Why? Well, I'll get to this later. There are other things that affect carbon dioxide levels like deforestation and cement production, et cetera. So even COVID shutting down so much industry slowed our emissions, but certainly didn't start to put it to the point where carbon dioxide levels are going down. All right. And so I've got various videos that try to depict it in different ways. Here's a bar graph where, we're keeping the city alight because of, coal being dug up, which I'll be discussing in just a second, petroleum. And as a result of all of the carbon to keep these lights on, if we were to go when carbon dioxide levels were first measured in the late 1950s, we do have measures prior to this, but now you're going back into ice and looking at gases and air bubbles trapped in ice. But the first direct measurements where someone said, how much carbon dioxide is in the air? Let's float a balloon, from the mountain and take a measurement. That was 1950s. So then it was a little over 300. All right. But then as time just goes on and on, it's just a steady increase. All right. Why? Well, somewhere. There we go. So there is a carbon cycle. All right. So here we see dry ice, carbon dioxide going. This is from the Mosquito Project, which some of us, serving on. So there's this cycle where carbon is in the air and the plants suck it out of the air to make organic molecules like sugar and protein and fats, et cetera. So this is carbon in the form of sugar, which is now inside living things, but it could come from gases. Here's carbon dioxide, here's methane. All right, so that's natural. So there's part of the cycle. And then animals can eat these plants. All right, and then they make animal stuff like animal proteins and the like. So you can eat plants, you can eat things from plants like nectar and the like. And so now animals have these biomolecules. Now, all of the living things, the animals and the plants, use the biomolecules. I mean, plants aren't doing this just for fun or to help the animals. They intend on getting the energy out. So there's something called cellular respiration, where you take sugar, you break it into 3 carbon molecules, and then you take that in your mitochondria to the Krebs cycle, that converts it into carbon dioxide. So I ate breakfast this morning, I eat carbon molecules. Right now, they're coming out my nose, all right, as carbon dioxide because of cellular respiration. This carbon, that carbon, that carbon currently coming out my nose started out in my breakfast. Plants do respiration, animals do respiration. And when animals and plants die, then there's respiration by the things that decompose them. So we have this cycle where carbon comes out of the air, it gets used by living things, and then one way or the other goes back into the air. All right, and so that's natural. The thing that changes is sometimes things get buried before they can decompose. All right, so where I am now, 350 million years ago, there were early forests here near the equator, and a lot of that was buried. And as a result, we have what's called coal. All right, so these early forests didn't get a chance to decompose, or maybe fungi weren't that good at decomposing wood yet. And so a lot of their buried stuff in the swamp mud just becomes what we call coal. So that carbon is trapped, no longer in the cycle. You're not in the carbon cycle if you're a mile underground. Okay, and the same thing with then petroleum, which is the carbon remains of marine life. All right, so you have all of this carbon which is trapped. And humans, to our credit, were pretty smart. We figured out I could burn that wood from the tree I cut down that was carbon in the carbon cycle, or I could then get old carbon, all right, from petroleum or from coal, burn that. The difference is this carbon has been out of the cycle for hundreds of millions of years. And then when we get electricity or we run our cars, it's now back. So these ships are full of carbon that has been out of the cycle for hundreds of millions of years. We run our cars, we generate electricity from coal, and now all of a sudden this buried carbon then comes back. All right, so that's one of the main reason that carbon dioxide levels are rising. All right, now I've got a bunch of videos. Let's go this one. And so one of my videos are a little sillier. I have an evil legion of climate change. So carbon dioxide ban, that's a factor. We have methane woman and nitrous oxider, which we'll get to. But another one here is deforester. All right, so I'd like to just kind of what's going on here. So here, when I went to the Peace Corps in South America, I just kind of figured there would be jungle everywhere. And now I realize that's a joke. There is jungle nowhere. If people can get there, this is what we find. It's cow pasture, right? But the thing is, this was jungle once. So if you were to weigh the jungle, which was once here, it would have weighed a lot. That's a lot of carbon, all right? If you were to weigh this now, much less. So when we cut down trees, all right, we take the carbon that otherwise would have been trapped in biomolecules, and that's now returned to the air. So while fossil fuel burning is the biggest source of the increase in carbon dioxide, deforestation is second. Cement making is third, and there are others. So this is why that even if we cut our emissions, and I'll get to this at the end, when I was born, there was about 3.5 billion people on the planet. Right, and then in the 1970s, there were 4, in the 1980s, there were 5, year 2000, there were 6, in the year 2011, there was 7. Sometime in the next year, they're going to announce that there's finally 8. 1 billion people use a lot of energy, and they also cut down a lot of trees. They need homes and agriculture, et cetera. And so the more and more of this that goes on as population grows, more and more carbon dioxide. So our carbon dioxide levels are going up. Unfortunately, there's more because other molecules trap heat as well, like methane. All right, and you may say, well, yeah, okay, but carbon dioxide, like that's the main one. All right, so this is easy to show. Methane's a heat trapping gas. And once again, you can just ask, does methane absorb infrared radiation in these windows? And it does. So this isn't up for debate. Methane absorbs infrared, and not only does it absorb infrared, but it absorbs in the spectrum where water doesn't, which means that water, which would otherwise go to space, is now around the planet, and the same is true of nitric oxide. All right, but there's not as much methane as carbon dioxide. That's true, but there's something known as global warming potential, where while all of these molecules are absorbing heat, some absorb more than others. So a kilogram of methane absorbs as much heat as 34 kilograms of carbon dioxide. So are there less methane emissions? Yes, but because methane is absorbing more, we have to take this very seriously. Nitrous oxide, there's less than carbon dioxide, but 1 kilogram of nitrous oxide warms the planet as much as almost 300 kilograms of carbon dioxide. And then every now and then you'll hear there's this regulation of a refrigerant or something. Why is the EPA regulating this? Well, this thing will warm, a kilogram warms as much as 1,500 kilograms of carbon dioxide. Sulfur hexafluoride, 32,000. And so getting back to those people looking scared, All right, so 2021 was a record year for carbon dioxide levels. Unfortunately, as we keep going up. So they're getting more and more shocking. If you look at methane levels, how do they change? Well, they go up and up and up. So pick a year, it's a record year for methane in the atmosphere as more and more is lost in the hydraulic fracturing process. Also, as more and more is released from cows. All right, so that sounds odd. And it sounds odd if you care about Earth's climate that you're measuring, say, cow flatulence. But if you were to take all of the wild mammals on the planet, put them on a scale, take all of the wild birds on the planet, put them on a scale, birds and reptiles, and then take livestock, the livestock far outweigh all of the wild vertebrates, I mean, other than the fish, I mean, the land vertebrates. There's an awful lot of cows, all right? And so the more methane that they are producing, and they produce a lot of methane, you know, once again, you add 1 billion people to the planet in 11 years, you've also added an awful lot of cows. That's a lot of new methane. You know, a lot of natural gas, that's a lot of methane. So methane levels just keep going up and up. Nitrous oxide, which we can release a couple of things like through fertilizers, levels just keep going up and up. That sulfur hexafluoride, all right, once again, the 132,000. Once again, 2021, the highest levels on record. And so just the heat trapping gases keep going up and up and up. So one would then predict, as we switch to the next kind of topic, one would then predict that temperature would increase. So let's look at that. Are temperatures increasing? Well, once again, there are different ways of measuring temperature. Some go back to the late 1800s. Once again, we could use more glacial estimates and go back further, but let's just use the direct measurements. And if you could look, the yellow line here is important. The yellow line is the average temperature of the 20th century. So out of every year, the average temperature of 1910 was measured, then 1920, then 1936, then 1945. You take the average temperature from the year 1900 to the year 2000, the average temperature of the 20th century, and let's make that the yellow bar. Let's say normal, or a normal. And then say, all right, now let's rank each year compared to that normal. Well, you'd see like in 1900 and 1905 and 1910, you see blue lines where that year was colder than normal. In fact, every year of the early 20th century was colder than that average, all right? Once you get in around 1940, you'll have some ups and downs. This year was a little warmer than that average. This year was a little cooler than that average. So for a couple of decades, all right, we're getting some years above, some years below, some years above, some years below. But by the time you get to 1977, every year since then is warmer than average. So is the climate warming? Well, once again, if we have an average, the 20th century being the average, since 1977, every year has been warmer than that. Now, once again, please just forgive me as I jump from video stuff. Jump from video to video, because if I try to make these say once every year, like in usually January when the new data is released, but I've got a bunch of these which say very similar things. So is it getting hotter? Let me show you 2 videos to kind of show that. If you ask what is the hottest year on record, well, let's say you asked that question in 1970. The hottest year on record, 1944, 1938, 53, 41. So a couple of decades represented here, the 60s, the 50s, the 40s, the 30s. All right, great. Let's ask that question again in 1980. And you say, all right, 1944, still really hot. 2 years in the 1970s there. Okay. So there were some hot years in the 70s. Ask that question in 1990. What were the hottest years on record? Almost all of them were in the 1980s. Ask that question in the year 2000. Wow, a couple 1980s, but now most of them were in the 1990s. Ask that question in the year 2000. 1998 still there. 1998 was really hot. But other than that, everything is in the year 2000. And it just keeps getting warmer and warmer. Like we're breaking records for the hottest years more and more frequently. Going back to this graph, as we look here, right, what's the hottest year on record? Once again, this data comes out each time. So we break the record here, we break the record there. Something happened in 2014. And once again, I apologize. I have a bunch of these. The question is, this one. 2014 was the warmest year on record until 2015, which was the warmest year on record, until 2016, which was then the warmest year on record. And never before at any point of this did 3 years in a row break the record for the hottest consecutive year. All right. So since then, and I'm sorry, I do have the one from last year. I just can't find it. All right. So I think this is it. So I've been pointing out by years. All right, but you could do it by months because, for example, here is, the average temperature during the month of August. So you see all of the hottest August have been recently, but you could do that every month. Here's the hottest Septembers. Here's the hottest, et cetera. So like, once again, I'm focusing on yearly averages, but you don't have to, you could do it month by month. The 10 hottest years have all occurred since 2010. So out of this record, which is, almost a century and a half, all 10 hottest years are since 2010. The 8 hottest years have all been the past 8 years. So are we seeing a trend? Well, we certainly are. So 2016 is the hottest year. 2020 is second. 2019 is third. All right. And so the trend is certainly to get hotter. What does that mean? Well, it means a lot of things. One, it means that ice is going to melt, and ice is melting everywhere. All right. So we can see, for example, there are glaciers. Here's the largest glacier in the contiguous United States, Mount Rainier, and it's melting. Now, doesn't this happen every year, especially during summer? It does, but it's happening faster. If you go to a glacier, you can see lines. This is where the glacier ended in this year. 10 years later, this is where the glacier ends. This is where the glacier ends, as you see it forming, this pool. And so all around the planet, we have glaciers which are receding. Mount Kilimanjaro may be ice-free in the near future in Africa. They're receding in the Andes, in Europe. If you want to see Glacier National Park in the United States, go now. It will soon be Muddy National Park, and there will be no glaciers left. So that ice is melting. Antarctica is melting. Now, Antarctica is tricky because it melts a little and it has land ice and sea ice, but it is, and every now and then really big chunks break off. So here was in 2002, satellites recorded that there was this chunk of ice, which then became water, which was 1.5 times the size of Orange County. That's a lot of ice when you think about how that size. Now, one of the things that's then a problem also with the Arctic, which I'll show you in a second, is this used to be white. White stuff reflects light. Sunlight hits it, bounces up into space. This is now blue. It absorbs. So that's the thing that scares me. All right, because many students, certainly not anyone listening to this, all right, but many students put things off until the very last moment. Like, this is due at midnight, 11:55. That's when we take it seriously. People tend to do that. When will we get serious about making changes for climate change? Well, let's wait till it starts to get really bad and then we'll fix our ways. All right. And if the changes are slowly, occurring in an incremental fashion, maybe that would work. But then some things occur in an exponential form, where it's a slow change, and then you hit this really steep part of a slope. And at that point, things are changing so quickly that that's not the time to initiate changes. You will not stop the spread of that. So things like this, where all of a sudden it starts to feed on itself, where not only is ice melting, but the more ice melts, the more heat the planet absorbs, that then starts to change the slope. That starts meaning that you get to a certain point and we're really not changing it. Now that was ice at the southern part. Let's take the northern part. So here at September 1980, the amount of, there's 2 months that are really good to pick. September, because that's the biggest Arctic extent. No, I'm sorry, the least. And then March, I believe, which is the most. So I've got videos on both of those. And so this is how much ice covered the Arctic in 1980. And just so that you don't think I picked one year because it was an outlier, here I go through every year. All right, and this is data that you can access because NOAA keeps track every day, every week, every month of what the ice extent is. So you can follow this, like, oh, what was ice extent last month, you know, et cetera. And as you can see, as the years go by, the ice tends to get less and less. So let's just pick September 1980, 7.9 million square kilometers. 89, 7.1. We get to 99, 6.3. All right, we get to September 2009, 5.4. All right, it just keeps going down and down. Now we're talking about millions of square kilometers. All right, so once again, because this is just continual, all right, which month you pick to compare, you know, because it's like weather. You'll have warmer years, colder years, wetter years, drier years. I've just, you know, it's kind of arbitrary in that sense. But there was one time I picked, and I forget, somewhere I say in this video which month it was. Which month was it? I forget. All right, but whatever month this was, the amount of ice from Antarctica, which had gone down since 1980, was 2.2 million square kilometers. The difference in the Arctic was 2.6. All right, Greenland, something I'll mention in a second. You put them together, the decreased amount of ice would cover most of, you know, the United States east of the Mississippi River. That's an awful lot of land that is no longer white and reflecting light, but now blue and absorbing light. All right. Greenland's the same thing. We have ice in Greenland, and if you were to take, you know, what, you know, the ice there, it has decreased, you know, here's every year, but if you want to take an average, 269 gigatons of ice less every year, all right, since 2002 when this was taken. And a gigaton is a billion metric tons, more than 2.2 trillion pounds. So that's a lot of ice, which is no longer there. And as it melts, this is going into the oceans, raising the levels of the ocean. So the planet is heating because the heat trapping gases are increasing, temperatures are going up, and then ice is melting. And if you were to look in 2020, you could do it every month. What's the ice extent in January? What's the ice extent in February? Once again, this is kind of arbitrary because we're seeing a trend. Whether you pick February, whether you pick March, whether you pick 2020 or 2021, it's the same thing. The ice just keeps going down and down. Well, then sea level must then be going up, and it is. All right, and so if you live in the Marshall Islands, you know that certain islands people are moving because they realize that there's a limited time while their island is still habitable. If you live in Miami, you know that there are certain times of the year where seawater is actually now intriguing, that you can find YouTube videos where someone's in a parking garage and there's an octopus underneath their car, because it's not just rainwater, which you're seeing at the corner of the parking garage, that's ocean water where it's untreated. And in Miami, they're redrawing street maps. You know, the ocean level begins to rise. You know, this part will no longer be, you know, habitable. We'll go to here. So sea level is certainly rising. But that's not what we will see first. And because I'm kind of a little inland from the coast, that's not what we will observe. What we will observe first is the changes in extreme weather. All right, so that affects all of us. And there has always been extreme weather, tornadoes and hurricanes and droughts, et cetera. But all of these are now getting worse. All right, so let me just kind of, you know, give just a little smattering of this, because once again, we could pick any year and talk about the hurricanes of that year or the droughts of that year. But if you, for example, you were to take the 2020 hurricane season and just say, all right, how many hurricanes were there, et cetera, you'd realize on record, 2020 was the worst. All right, more hurricanes in 2020 than any other year. 2020 wildfire season, it was one of the 3 worst, with almost 10 million acres burned. And when we say worst, that would then vary from state to state. So this year was the worst wildfire season in Colorado, but the 3rd worst in Utah. The next year was the worst in Utah, the 2nd worst in Colorado, et cetera. But the points are that this climate change affects us in many ways. As the ocean gets warmer, a big storm like a hurricane finds it then easier to absorb water. So there have always been hurricanes, but now they're bigger. They last longer and they carry more water. All right. And so now, for example, whether we talk about, Hurricane Katrina, which hit Florida and then went down to a Category 1. It was tiny then. But then the Gulf was super warm that year. And then as it went on this side of Florida, it was able to pick up, speed and size again much more quickly than it would have in a typical year. And so as we look at these, climate change is not necessarily causing these hurricanes. It's just making them, more frequent and bigger. All right. And so those are certainly issues. And then each of these can be devastating in their own ways, depending on the track that they hit. So for example, the Hurricane Maria, which hit Puerto Rico, okay. Once again, it was a Category 5 when it struck Dominica. It was a Category 4 when it hit Puerto Rico. Almost a year after the hurricane, the death toll was raised to almost 3,000. Some estimated it was higher to 5,000. And a year later, there were so many people who still had, these blue tarps over their houses. And so when we talk about, the effects that things have, if your power goes out, well, that affects the hospital. All right, that affects, the rate at which diseases spread, et cetera. And once again, these are things that you can read, reported all of the effects of climate change. But if you were, as I did, going to fly out, a year later, you'd see how many roofs were still damaged. And so far as, an individual's ability to be resistant to disease, if your roof is a plastic tarp for a year, obviously, as you can see, all of the blue tarps here. Now, obviously, this is exposing you to other dangers as well. All right. So here in the East, hurricanes and too much water, that's a problem. Obviously, then there are places on Earth where too little water is the problem. So as you get drier and drier years, that then makes it more challenging for plants to grow. It's hotter, it's drier. Also, it limits winter. Winter is shorter and less cold, which means that the really cold temperatures, which usually kill such and such percentage of the beetles, now is killing less. So now there are beetle infestations which kill all the wood. So not only are you hot and dry, but now you've got far more dead trees than you usually do. All right, and so now wildfire incidence is going to go up. All right, so if we look, this will obviously vary from year to year, just like water precipitation. But in general, if we were to look at millions of acres burned by wildfires in the United States, there is a trend going upwards. If we look at the areas which are in drought, all right, we have areas which we say they are in drought, severe drought, extreme drought, exceptional drought, and once again, if we go to this state, there's a record, in this year, we go to another state, it's a record in this year. But the overall trend is certainly things are becoming drier and drier. Okay. So by the middle of 2021, almost half of the contiguous United States was experiencing somewhere between moderate and exceptional drought. So while there are certainly variations from year to year, all right, this is clearly outside the norm. Some states saw their worst droughts ever. All right. So once again, we could focus on each year, the wildfire season. So for example, 2020 was very bad. Last year, 2021, was not quite as bad as that, but still more than 54,000 fires burned an area of 6.8 million acres, the size of Massachusetts, including 3 of the top 20 in California. Each one is devastating. So for example, there is a type of tree, which is native to the Southwest, called the Joshua tree that you would find in, say, Joshua Tree National Park, and also Mojave National Preserve. All right, so it's a very unique tree. All right, and then a year and a half ago, a fire. So this is what they look like. And then this is what they shouldn't look like. All right, but in 2020, a lightning strike started what's called the Dome Fire, and 43,000 acres burned, killing 1.3 million trees. Now, just to stress, this is the only part of the world where these trees are from. All right, and so you just go on just mile after mile. And this is one fire. Remember, there were 54,000, all right, in 2021, and this was 2020 where there was even more. So each fire has its own story. Each hurricane has its own story. All right, and another way to measure this, if you want it, is how many disasters cost $1 billion? All right, well, because that affects all of us. I mean, not only does it affect the people who live there, but as we talk about whether it be insurance or federal money to help people recover, these are some of which we're all paying. The number of billion-dollar disasters keeps going up year after year. All right, and so that's another thing. If you want to say how many disasters last year were $1 billion, somewhere I have. So anyway, we are going up and up here. All right, so there's those aspects. Now, before I kind of switch gears. This was something on spring break. One of the things I wanted to do was just to be able to teach this better, because there are things that I know, but without the pictures, I can't tell the story. So here's the story. So here is Las Vegas. All right. Las Vegas, growing part of the Southwest, actually all of the Southwest, lots more and more people there. They need water, actually. First. And it turns out 90% of the water of Las Vegas comes from Lake Mead. Lake Mead is the largest reservoir in the country. The Colorado River was dammed by the Hoover Dam, all right, creating our nation's largest reservoir. All right, so here you see Lake Mead. All right, I'm lying. That's not Lake Mead. That's what Lake Mead looked like 20 years ago. 20 years ago, Lake Mead looked like this. All right, now what does Lake Mead look like? It looks like that. The water level has gone down 140 feet. All right, it is only a third full since the year 2000, I think like 2002. All right, 20 years, we've gone down this much. Now, the Hoover Dam generates so much electricity for the Southwest, but part of that is all of the pressure from all of this water. You decrease the water, you decrease the pressure, electrical production has decreased by about a quarter. So here's, once again, that slope increasing. As we burn more fossil fuels, climate change will get worse. Now, hydroelectric power will mean we'll burn less fossil fuels, but as climate change worsens, Hoover Dam is generating less and less hydroelectric power. That's more and more fossil fuels that people will be using instead. All right, so here's a story to be told. This huge lake. If we were to just look at it year, this is the year 2000 going here. It's some years there's a little more rain or a little more snowpack, in the Colorado River, et cetera. But there has been a steady decrease. If it were to go down like another 170 feet, all right, the Hoover Dam, no water goes over it. All right, so the change we've seen in the past 20 years, if that's what the next 20 years holds, well, Las Vegas is drawing its water from what comes out the other side. All right, this is generating electricity and water is no longer going over the dam. So this is certainly an issue. Now, it's an issue, so many things. It's an issue for hydroelectric production, for drinking, Lake Mead's drinking water, but even just recreation. All right, so I mean, here you have an arid region. All right, and you've got this huge lake. So people love it for fishing, for boating, for hiking, for camping. What's not to love about a big lake in an arid area? Oh, and I'm sorry, by the way, luckily in the 1970s, I think, they redid a lot of these water intakes. If they hadn't, then I think what I read is Hoover Dam already wouldn't be producing any electricity. All right, because look at all of this, where water used to come in to, drive the turbines, obviously now dry. All right. Now, obviously, recreation here is an issue Because where do you launch your boats from, right? The lake used to go up to here, what's called the bathtub ring. This was when the sediments from the Colorado River, stained the rocks here. That's where the lake used to be, both in height and land. So every year, the Park Service is moving the docks, all right, because the lake level keeps retreating until they get to certain points where this is no longer a boat launch. All right, so I've got videos, but just a short version is there is still like a little narrow way to get out to Lake Mead from here, but it's so shallow that this used to be a really big area where boats were launched from, et cetera, and now it's just closed. All right, you can't launch a boat from here. There are like all of these floats along here that say no boats. So originally it meant that, the boat that's floating out here, you can't go beyond this pylon over to here. But now, it's ironic, no boats, period. The thing is closed because now this is dry land. So once again, this was where boats were and fishes were. When you go, here, you see nothing but shellfish, you can find, lures, et cetera. Actually, one of the problems is broken glass. Because for decades, people would be drinking on their boats and tossing water bottles into Lake Mead. If you want to go, swimming on any of the beaches now, you have to wear shoes because there's so much glass that water that you'll cut your feet. Here's a weird question before I start shifting gears to oceans and winding down. Lake Tahoe is the biggest area, the second largest inland body of water in California. There's another area that's bigger, the first biggest. I had never heard of. It's called the Salton Sea. Here's the Salton Sea. And just here's an idea of how complex this can be. So here's a question where there's no easy answers, at least none that are obvious to me. So is this natural? Well, years and years ago, maybe, not lately. So this was dry, all right, but it's also below sea level because it's on a fall. And when people screwed up the irrigation, water, went over the banks and flooded this area. So now all of a sudden, this area that used to be dry now has water. So this big inland lake, and if this is East California, it's hot. And what's not to love about a big lake? People loved it, big tourist place. The Beach Boys came there, Frank Sinatra came there, great. But because it's so hot, the water keeps evaporating, the salt stays behind, and now it's twice the salinity as the Pacific Ocean. And because now it keeps shrinking because the water levels are going down, it's exposing this playa, which is lots and lots of salt, but also lots and lots of chemicals used from the agriculture. It's toxic, all right? You don't want to be near here. And the people who live here, all right, their rates of asthma and respiratory diseases far higher than the surrounding area, like Palm Springs, which isn't that far away, and a lot of environmental justice. I mean, the people who live around Salton Sea are not the same people who live in Palm Springs. All right, so what do? Well, we could throw more water here and more money, all right, but it's kind of toxic. It's not really serving any thing. And in a water shortage, part of you don't want to do that. But if you don't do that, it's going to get much worse as more evaporates, exposing more chemicals. Also, California has used all of its wetlands for, irrigating farms. Where do the migrating birds go? The Salton Sea is not great, but it's something. All right, if that goes, now there's nothing. So if you throw money and water at the Salton Sea, that's maybe not the best use of water and money. But if you don't, it'll just get worse. So what's the answer? I don't know. All right. Now that water is important, all right, but obviously other water is as well, like the oceans. As we put more and more carbon dioxide in the air, that means there's more and more carbonic acid. So carbon dioxide plus water gives you carbonic acid, all right? And it's just easy to show if you have a little cup where it will change color when you make it more acid. If you blow bubbles through a straw into water, it changes color because the carbon dioxide from your exhaled air becomes carbonic acid. All right, so that's just, basic. Problem is, as oceans acidify, that has lots of negative effects, especially on the corals. All right, so corals, actually, let me go to corals. I'm sorry, I've got lots of, so it affects lots of things, microscopic life, there we go. But it affects corals. There's not a lot of coral reef in the world. There's a lot of ocean, all right? I mean, there's a lot of ocean on our planet, but if you were to put all of the coral reef in one place, it would equal the size of New York, Pennsylvania, and New Jersey. And when you consider the size of the oceans, that's not huge, All right, so there's not a lot of coral reef, but look at the coral reefs. Oh, that's where you have so much life. About a quarter of the ocean's fish spend at least some time in a coral reef. All right, so this is like the rainforest underwater. So these are the most biodiverse places of the ocean. People rely on this for protein if they eat fish. Southeast Asia, fish is a major source of protein. But if you go to the Caribbean, tourism is, the driving force of GDP, and people coming to snorkel and, scuba dive here, that is, a major driving force. But climate change is worsening. So this is bleached coral. This used to look like the corals that you just saw. But when the oceans become more acidic, that hurts the corals. When the oceans become warmer, that hurts the corals. When there are more severe storms, that hurts, the corals. And the sum of all of these effects, coral reefs all over the world are bleaching and dying, which is having devastating impacts on the fish populations. So there's that. And, we could go on. I'm going to start to tie up. But all of these unexpected effects. So for example, nuclear power, all right, one of the things it doesn't do is produce carbon dioxide. All right, so it is a renewable sense. It doesn't produce carbon dioxide, but you have to be able to cool the reactors. And as waters warm, you get to the point where nuclear reactors have to cut down production just because the water that they would need to cool is just too hot. So once again, now you would burn more fossil fuel there. Once again, this is just kind of a random effects. I like to ski. And in February 2017, all right, here's me in a kayak looking at a bald eagle, which is weird, all right, because the lake should be frozen and the eagle should be nowhere near her because they can't fish on ice. All right, but nevertheless, here I was. This isn't what February lakes should look like in this area, but there I am. And then I went skiing. All right, February should be, the most pristine times for skiing, but the ski slopes had to shut down for a bit. Some shut down for the year. And if you look, you had to be careful because that's not, pure snow anymore. Obviously, you're seeing, muddy patches there. So climate change is going to affect all of these people differently. All right, so if you have a ski slope, or if you like ice fishing, et cetera, it's going to affect you. If you like planting, all right, well, it's going to affect you because if you take an old gardening guide, all right, and you say, what can you plant in this area? You say, oh, you're in zone whatever, you can plant these bulbs. Well, 20 years later, you're in a different zone. Climate has changed to the point where the plants that you can grow here are different than they were 20 years ago. When are the days which are frost-free, which are important for plants? Well, when do you have the last frost, et cetera? The time is changing. So climate change is having all of these diverse effects. Now, the last thing very quickly, and then tie up, I mentioned population, and that's driving, oh, I'm sorry, before I do population, I'm sorry, there's one last thing. Climate change can kill you, all right? And not only are we talking about hurricanes and wildfires, et cetera, but if you look at air pollution, a lot of people, just air pollution doesn't hit them as a bad thing because when you look at the deadliest things on earth, you see, oh, heart disease, stroke, respiratory diseases like asthma, not realizing that these are worse with air pollution. All right, so our Clean Air Act is thought to help, hundreds of thousands of premature deaths. So for example, in Paraguay, I had a nephew who died of his asthma because of the air that he was breathing, especially in his workplace. And if you look at studies, all right, people who estimate like how many premature deaths occur every year because of air pollution, it's in the millions. Now that sounds weird to you, and that's good. All right, the reason it sounds weird is because most of those people don't live in the United States. We have actually very good legislation cleaning your air, and lots of people on Earth grow up where that's not the case. So millions of people are already affected by air pollution, where it causes premature heart attacks, premature strokes. If you live near a city, or if you live anywhere, if you're working in a hospital and the weather forecast in the summers, there's a heat wave and the ozone index is up, then the hospital knows we need more staff. all right, because emergency rooms will spike during this time. That's just what happens in heat waves when there's a lot of air pollution. And climate change is now making this worse. Out west, there's more and more wildfires, more and more particulate pollution. Heck, there was one day last summer, whereas if you looked in the sky in Orange County in New York, it was hazy because of the wildfires out west, all right, affecting our air quality. All right, and so, when we look at the effects of climate change, it's all of these things. And as our population gets bigger and bigger, this problem isn't going away. If we've just added 1 billion people to the planet since the year 2011, well, those people need homes and food and energy and air conditioning if they live in cold places, heating if they live in warm places. That's more fossil fuels. 1 billion people, that's 3 United States, just added in the last 11 years. So what to do? Well, we should do something quickly. And certainly there's things that you can do as an individual. All right, so you could just call your electric provider and say, hey, could you switch me from provider A to provider B, because provider B is providing energy primarily from wind. All right, and so you could say the electricity in my house, it's not burning fossil fuels. My house it's a little more expensive, prices keep coming down, but nevertheless, wind is powering my house. All right, if you were to purchase an appliance, get an Energy Star appliance. All right, is it a little more expensive? Yeah, it often is. But then if you count the energy savings over the life of the appliance, you've saved money. You maybe put a little more out in the beginning, but you end up saving money. And now that was less, fuel that you used or water that you used, et cetera. Same thing with, a hybrid car. I drive a hybrid car. It costs a little extra money at the outset, but I have gotten 70 miles per gallon since I've gotten it. So the money that I've saved on gas, it will pay for itself. And the fact that I'm plugging it in, from my house, wind energy is powering a lot of my car. Another big thing that we can do is just, how do we eat? All right, so cows use an enormous amount of fossil fuels, just to, what feeds them, et cetera, all of the fertilizers and the like. And so what we eat affects our carbon footprint. And so if you were to have meatless Mondays, eat a little less meat, even just one day a week, that would make a difference. If you would eat less beef and eat another protein source, that would make a difference. If you become vegetarian or vegan, even better. So all of these things are things that individuals can do. But some of this is just too big for individuals. I mean, by all means, do your part. All right, but then as far as, acting in your community and, taking this into consideration, when you vote, a lot of these are problems which, larger organizations and governments are going to be needed in order to address. And then finally, all of us are concerned about, not only what the world will look like in our lifetimes, but then, the next generation, the one after that. We are in this together, all right? And then so there is a lot of reason for concern. I mean, a lot of things are going in the wrong direction. And the only thing I say to some of my classes at the very end is when you consider the human brain, without exaggeration, this is the most complex structure in the known universe. We don't know of anything which has ever existed more complex than this. If our great, creativity has it allowed us to, manipulate the world so that we've created this problem, then there's the hope that, our great creativity will help us realize the magnitude of it and then realize, solutions to it. So that was my thoughts on climate change in 2022. Does anybody have any questions? Yeah.
Just have one comment when you were talking about the air pollution. I think it was about half a dozen years ago. My husband and I went to California where our oldest son's baseball team was playing. And it was in Los Angeles. And you could see the pollution as we drove towards that. I had never experienced that in real life. I mean, I've seen it on television, but it's just horrendous. It's like a gray cloud coming down. And so they definitely are being affected.
There are so many anecdotal things. Like if you look at a map from above, you can tell where China and India are on a map from above because you can see the gray, or you can just look above.
Remember when the pandemic first shut everybody down and they were showing those maps on how pollution was being almost eliminated in some of these countries. They could actually, India could see the stars again. But I just didn't, the only reason why I made that comment is that I don't think our country is free of it by any means.
No.
It's not as bad as
Right.
others, but, and then of course in China, with all the computers, our computers that go over there, to be destroyed, we're killing another population of the pollution. It's horrendous.
Excellent point. And what you talk about other countries, something I worry about is, to a large extent, I use, and that was another video here, I use far more carbon dioxide than is my share. I mean, I try to conserve, but compare me to someone who lives in India or whatever, per capita, I use far more. So climate change affects all of us, but the rich countries have produced far more of the problem. And so when we talk about environmental justice, so whether you look at the whole country, China producing far more carbon dioxide than the United States, than India, than all of these others. But if you look at number of metric tons that an average American like myself put into the air last, 15 metric tons just because of me. All right. But you look at the rest of the world, it's so much less. They'll suffer from climate change, but it primarily wasn't them. It was primarily those, living in the more developed countries producing far more than their share. So as far as environmental justice, that's another piece of it. Anything else?
But we do. How do we get people to act?
So that's so I don't know, and I never prepare. The one thing that we are entering an election year, and I'm not going to try to get political, but the one thing, and just here's, I don't understand. If you were to ask what are going to be the top issues of this next year, like what are the big political issues that people are upset about, I don't understand why this isn't there. The fact that the Colorado River's water is being rationed among states and among Arizona getting a lot less, I don't know why that isn't the top. When you have so much drought and wildfire and you have so many more hurricanes, et cetera, and you ask people what are you voting on the basis of, this isn't it. But this is more likely to directly impact you than any of the things that I think a lot of people do list. So I don't know whether we're more vocal in that sense. I don't know. Sometimes you say things like that and it doesn't register, and you don't know why. Like, why is anyway? So once again, not to get blue. So each of us can make our own individual contributions, but at a certain sense, if you could be active in your community, and certainly can think of these issues when you vote, that certainly has a role. Well, thank you all for coming, and I hope you enjoy our week with Earth Day, etc. Okay. Fair.